Swayam Prabha. Digital India. Educated India.
Welcome to the second lesson of the sixth module, which is on stresses in beams part 2. In fact, in the last lesson of this particular module, we have discussed the effect of the bending and consequently the stresses in a beam due to bending, and we have seen that how to evaluate stress at any point due to the loads which are acting on the beam, and consequently if it is acted on by pure bending, then what will be the stresses. Now, which we have defined as the bending equation or the flexure equation. Now, we will be looking into some more aspects of the bending stresses if they act on a section which is symmetrical with respect to the vertical axis, but could be unsymmetrical with respect to horizontal x axis or z axis which we have defined. Let us look into then that once this particular lesson is completed, one should be able to understand the effect of bending stress in beams of different cross section which are symmetrical about vertical axis, but could be unsymmetrical with respect to the horizontal axis. One should be able to understand the concept of economical section. Now, we will look into the sections which are more appropriate when they will be subjected to bending, which we can call as most economical section, and one should be in a position to evaluate bending stress in beams of different cross sections for different loadings. Hence, the scope of this particular lesson includes the recapitulation of previous lessons or just the previous lesson which we have discussed, evaluation of bending stress in beams of different cross section with vertical axis of symmetry, some relevant information with regard to bending stresses in beams. Now, we will look into that. We have derived the flexural equation or the bending equation. Now, what are the consequences of that? What are the consequences of bending stresses? What are the impact of bending stresses on different type of cross section? That we will look into, and we will be looking into some examples for evaluating bending stresses in beams. Well, let us look into the answers of the questions which I gave you last time. The first question was, what are the assumptions made in evaluating bending stress in a beam? Now, this particular aspect let us discuss with respect to the diagram which I discussed last time in the last lesson. If you remember, this is a segment of a beam, the section of which is a cross section of the beam is something like a trapezium, which is symmetrical with respect to the vertical axis and unsymmetrical with respect to the horizontal axis. So, here we assume that the beam has an axial plane of symmetry and xy plane is the axial plane of symmetry, and the loads which act on the beam, they lie in the plane of symmetry. Also, it is assumed that the axis of the beam bends, but it does not stretch, which we have seen last time while deriving the flexural equation, that because of the load which lies in the plane of this symmetry, this beam undergoes bending, the axis of the beam undergoes bending, but it does not stretches. And the most important one is that the plane sections remain plane and perpendicular to the deformed axis of the bulk. That means, when the beam is subjected to loads, it undergoes bending. The axis of the beam undergoes bending, it does not stretch, and the cross sections, any cross section we take at any location of the beam, the section remains plane, it does not deform, and it becomes perpendicular to the deformed axis, and this is the main assumption while deriving the flexural equation. Now, the second question was what is the bending equation. Now, this you know we had derived last time, that m by I is equals to E by rho is equals to sigma by y. Now, this we call as the bending equation or the flexural equation. Now, where m is the bending moment, I we call as the moment of inertia of the cross section, E is the modulus of elasticity, rho is the radius of curvature of the axis of the beam, sigma is the bending stress, and y is the point where we are trying to find out the stress. So, from this particular equation you see we can write m by I is equals to minus sigma by y, or this gives sigma as equals to minus m y by I. Now, sigma we call as the bending stress, m is the bending moment, I is the moment of inertia, and y is the distance at the point at which we are evaluating the stress. Now, if you look into this particular equation, it has a similarity with the equation which we had derived when a bar was subjected to a twisting moment, where the twisting moment was T and T by J was equals to tau by rho equals to G theta by L. Tau was the shear stress, so which is corresponding to the sigma here when we are talking about bending. Now, so T can be comparable, twisting moment can be comparable with the bending moment, shear stress can be comparable with tau, J the polar moment of inertia can be comparable with the moment of inertia of the section. Now, T by J was equals to tau by rho, rho was the radius of the shaft equals to G theta by L, that was the rotation. Now, here it is in terms of curvature, 1 by rho, rho is the radius of the curvature, and 1 by rho term we call as kappa, which is curvature of the beam. So, it has a similarity between the torsion equation and the bending equation. Of course, the terms have different meaning, and please note here that the sectional parameters, like in case of twisting moment when it was acting on a shaft, we had used the polar moment of inertia J, which is corresponding to the sectional property. Now, in this particular case when we are dealing with bending, we are again dealing with the sectional properties, but we are computing the moment of inertia which is lying which is about the axis lying in the plane of the cross section. So, now the question is, when we have this bending moment as positive, as we have assumed in this particular derivation, that this is positive moment corresponding to this kind of configuration. When this is positive, then stress, if y is positive, then stress is equals to negative, which means this cos and this y is positive when we are talking about the upward direction, this is y and this is z. So, this is y is positive upward. So, at the upward point, at the extreme point, we have a stress which is negative, and as you can see physically that because of this kind of bending, the top fiber undergoes a compression. So, the negative means the compressive stress and the positive, thereby corresponding to this particular equation, taking m as positive and y if we take negative on the bottom side, then this becomes positive, stress becomes positive, which corresponds to the stress at the bottom fiber. So, we have, when we get sigma as negative, then we call that as compressive stress, and when sigma we get as positive, we call that as tensile stress, and this can be verified corresponding to this configuration where the moment here is negative, m is negative, because it is in the opposite direction than we have assumed as positive. Now, if m is negative, now when y is positive over here, so since m is negative, sigma becomes positive, and according to our convention, when sigma is positive, it is tensile, and physically as you can see that because of this kind of moment, the top fiber undergoes stretching, which is tensile in nature. And correspondingly the bottom fiber undergoes a compressive stress. So, that is how we decide about the tensile or the compressive stress in a beam when they are subjected to load, depending on whether they are having positive or negative moment, and mind that the positive moment is the moment which we have assumed on the right face when it is in anticlockwise direction. Now, the last question was that how do you locate neutral axis in a given cross section of a beam. Now, here first of all we should know that what we really mean by the neutral axis. Now, if you remember that when we were deriving the flexural equation, we said that summation of Fx equals to 0 for equilibrium, and that gave us that minus E by rho integral y dA is equals to 0. Now, this being constant, let us say that we call this as A y bar equals to 0. This indicates that the y bar, the distance of the centroid of the cross section with reference to the origin, if it is 0, then the summation of Fx will be 0. So, in effect it means that the axis must pass through the centroid, the z axis must pass through the centroid of the cross section. Now, when y is equals to 0, as we had seen that epsilon is equals to minus y by rho, and correspondingly stress is equals to E times epsilon. So, minus E times y by rho. Now, when y is equals to 0, so correspondingly E and epsilon and sigma will be 0 at that particular point, and along this axis the strain, if we call this as a strain diagram and this is the stress diagram, then at this axis we find that the strain and the stress is 0, and the strain and the stress has a linear variation as a function of y, and it varies linearly with respect to 0 over here and varies linearly the stress with respect to 0 here. So, this is the stress distribution, and according to our positive moment which is acting about this particular axis, we have a compressive stress here and tensile stress over here. So, if we call this stress sigma, sigma compression and sigma tension. Now, so the condition for 0 axial force in the section can be satisfied only if the neutral axis passes through the centroid of the cross section. Now, we call this as neutral axis because along this axis the stress and the strain is 0 in the beam cross section, and this can be satisfied if the neutral axis passes through the centroid, then there will not be any axial force in the beam, and this is one of the requirement of the equilibrium criteria. Hence, the neutral axis along the axis where the stress is 0 must lie in the centroid if it has to satisfy that there is no axial force in the beam. Well, then after looking into the answers of the questions, let us look into some of the aspects on the bending equation which we have derived last time. Now, if the cross section of the beam is a symmetrical one, now please keep in mind that we are using the cross sections which are symmetrical with respect to the vertical axis. Now, with regard to the horizontal axis, it could be symmetrical, it could be unsymmetrical. Now, let us consider these two cases, that if the section is symmetrical even with respect to the horizontal axis, then what happens, or if it is unsymmetrical, then what is the consequence. Now, if the cross section is symmetrical with respect to the horizontal axis, as in the case of a rectangular or a square section, wherein the extreme distance of the fiber with respect to this is equal, because it is symmetrical, the centroid lies the two axes passes through the centroid, and centroid divides the whole depth equally. So, the top distance also is y and this is minus y. So, the stress which we will get at the top for the symmetrical ones, sigma, is equals to minus m times y by I, which is m is positive and we get the stress as negative, which is compressive at the top. Now, if we have y as negative at the bottom, then this is going to be equals to m y by I, and this is a positive quantity which is a tensile at the bottom. But interestingly, whatever is the compressive or tensile as the stresses, the magnitude wise if they will be the same for the same value of m, because y is identical. So, the bending compressive stress and the bending tensile stress for the symmetrical section, they will be the same. The section which is symmetrical about both the axes, about the vertical axis as well as the horizontal axis, the bending stress which we compute at the top, which is bending compressive stress, and the bending tensile stress at the bottom, magnitude wise they are the same. Now, if we consider an unsymmetrical section where the section is symmetrical with respect to the vertical, but it is not symmetrical with respect to the horizontal axis, such as in this particular case, as you can see that the distance of the fibers from here and the distance of this is different. Now, so this is the, but this is the location of the centroid of the cross section. So, first thing what we do is that we locate the position of the centroid for a section, and as we have seen that if there is no axial force in the beam, then the neutral axis must pass through the centroid. So, once we locate the position of the centroid, then the position of the neutral axis is known to us, and then the distribution of the strain and the stress with respect to this, this will be 0 and some value over here and some value over here, because the distribution is a linear one. So, the distribution of the strain or the stress will be a linear distribution with respect to the 0 strain and the stress along the neutral axis. So, here now since y1 bar and y2 bar, the distances of the extreme fiber from the neutral axis, they are different. Now, corresponding to the bending moment whatever we will have, this is our positive bending moment, the stress sigma will be equals to m y by I, which is minus. Now, for the top fiber, the y is equals to y2 bar. So, this is equals to minus m y2 bar by I, and if m is positive, then this quantity is negative and this is compressive stress. Now, for sigma, this is sigma top. Now, sigma at the bottom, this is equals to m minus m y by I, and y will be negative from with respect to this, which is minus y1 bar. So, this is going to be a positive quantity m y1 bar by I, and this stress according to our nomenclature, this is tensile stress. But the magnitude of this compressive stress at the top and the magnitude of the tensile stress at the bottom, they will be different. Though the magnitude of the bending moment which is acting in the beam at a particular cross section, if we know the value m, then when we compute the stresses, since the section is not symmetrical with respect to the horizontal axis, the compressive and the tensile stresses which will be obtaining for a particular moment, they will be different. Thirdly, the units of the stress that you can readily look into from this expression, that sigma is equals to m y by I respective of the sign. M is in Newton meter, y is in meter, and I the moment of inertia, second moment of area, which is meter to the power 4. So, this gives us in Newton per meter square, so which is nothing but Pascal. So, sigma we represent in terms of Pascal or megapascal or gigapascal. Now, lastly, the most important thing is the applicability of this bending formula. Now, if you remember, while deriving this bending equation, we had assumed that the segment of the beam is subjected to a pure bending. Now, in normal situation, when a beam is subjected to loading, they will be subjected to bending moment, and in some zones there could be bending moment associated with the shear force. Now, when we have derived the bending formula which is subjected to a pure bending, we have assumed that the plane sections remain plane. Now, it may so happen that when along with the bending the shear force also is acting at a particular section, the assumption of plane sections remaining plane may not be truly satisfied. Now, if that happens, then if we compute the stresses, that will not be right using this bending equation. But in general, when we talk about the beam, it has its length is much larger in comparison to its cross sectional dimension, and hence the error which we get in evaluating the stresses with this particular assumption is insignificant and we can neglect that. Hence, we can apply this bending equation even if we do not have pure bending in a particular segment of the beam. If the bending is non-uniform, it is not uniform, even then we can employ this equation without losing much of accuracy in the analysis of the stress. So, this is very important that though we are deriving the equation in terms of the pure bending moment, we can apply this equation in other areas as well, where the beam is not truly acted on by the pure bending. Now, let us look into another aspect which is important, that we were dealing with a section which is like symmetrical with respect to the vertical axis and could be unsymmetrical or symmetrical with respect to the horizontal axis. Also, we have seen the distribution of the stress. Now, if you have noticed it, you see that we get 0 stress at the neutral axis and then it has a linear variation. So, the maximum intensity of stresses that occur is towards the outer fiber. Now, so this particular part of the beam really is not utilized because it is not fully stressed, hence this is not going to be utilized to the extent and naturally it becomes uneconomical. That is number 1. Number 2 is that if you have larger concentration of area away from the neutral axis, then the contribution in the moment of inertia for that area will be larger, because we are calculating the second moment of area, which is a y square. So, the larger the distance from the neutral axis, you will have larger contribution in the moment of inertia. Hence, instead of having the masses concentrated near the neutral axis, if we can take away the mass away from the neutral axis, we can have larger effect, and that is what is demonstrated over here. Now, in this particular rectangular section, we have a dimension of 100 millimeter width and 300 millimeter depth. So, the area, cross sectional area of this is equals to 300 times 100 millimeter square. Now, let us say we utilize the same area, but we place the masses in such a way that they are at a distance apart from the neutral axis. This is the neutral axis. Now, the width of this particular segment is 300 millimeter and the width and the depth is 50 millimeter, and we have two such segments which are away from the neutral axis. Now, if we look into the area wise, we have 2 into 300 into 50. So, we have identical area as that of the first one. Now, when we compute the moment of inertia I, and then consequently if we divide this I by the extreme distance, which is y, I by y, we call this quantity as z, which we generally define as the section modulus. Now, if we compute I in this particular case and divide this by this extreme distance y, I by y, the value of I by y which we get in this particular case and the value of I by y which we get in this particular case, if you look into, you will see that when the segments are a distance apart from the neutral axis, we get a value of z which is almost more than 2 times of this value. So, this shows that if we can concentrate the mass away from the neutral axis, then we can get the larger contribution in the moment of inertia. And as we know that the stress sigma is equals to m y by I or m by z. So, larger the value of z, then lower will be the stresses, and naturally if we know that the intensity of the stress a particular member can be subjected to, the allowable stress in the material, then if we can keep the stress level lower than the allowable limit, naturally that particular member will be more efficient. So, larger the value of the z, larger will be the moment carrying capacity, because the stress level will be lower. So, we can put more load in such beams. So, if we have a section wherein we can lump the mass away from the neutral axis, then that kind of section becomes more efficient. But then we cannot keep these two segments just freely a distance apart without having any connection between the two, because to act the two units integrally we need to have some kind of a connection between the two. So, that means some material is necessary to interconnect these two. Now, if we can have this kind of a section which is similar to an I section, this becomes more efficient in comparison to a rectangular section having the same area. That means, if we have the same area for a rectangular section vis-a-vis if we take an I section having the similar area with the same depth, we find that an I section will be more efficient in comparison to a rectangular section, so far as the bending stress transfer is concerned. Well, then having looked into this, let us look into some of the examples related to this, how do we evaluate the bending stresses. Now, here we have an example in which this is a simply supported beam which is hinged at end A and is supported on roller at end B, subjected to uniformly distributed load of 3 kilonewton per meter over the entire length, and has a concentrated load P which is at a distance of 4 meter from support A. Now, in fact, this particular example was given to you last time and I hope that you have done it. Let us look into the aspects that how do we solve this particular problem. Now, what we need to do is that we will have to determine the largest allowable value of P if the bending stress is limited to 10 MPa, and here the cross section of the beam is a rectangular one having width 120 millimeter and depth as 400 millimeter. Now, as usual we evaluate the reactive forces as you know that at A we will have a vertical reaction Ra, we will have a horizontal reaction Ha because this is a hinge, and at the roller support we will have a vertical reaction Rb, but since there are no horizontal forces Ha will be equals to 0. So, we will have only Ra and Rb, and if you look into this particular example that it has uniformly distributed load over the entire span and a concentrated load P. Now, if we separate out these two loading, now as you know that we are dealing with the stresses within the elastic limit, hence we can individually calculate the effect of these two different loads and can superpose them, we will get the same effect if we take the combined loading. So, we have seen that for uniformly distributed load the reactive values will be half of the total load, and this for the concentrated load we can take in proportion to the distances. So, if we compute the value of these reactive forces, then Ra will be equals to 3 times 4 plus 1 5, total length is 5 meter. So, 15 by 2 which is 7.5 because of uniformly distributed load, plus because of P the value of Ra if we take the moment of this will be P times 1 by 5. So, plus P by 5 will be the value of Ra. Now, Rb correspondingly will be 3 times 5 means 15 plus P minus 7.5 minus P by 5. So, Rb consequently will be equals to 7.5 plus 4 P by 5. So, these are the values of the reactive forces Ra and Rb. Now, interesting part in this particular case is that we will have to find out the value of P for which the maximum value of P for which the bending stress is limited to 10 MPa cannot exceed a value of 10 megapascal. Now, when you have this kind of a loading as we have seen in the past, that if we like to draw the shear force diagram, because we will have to first locate the position where we get the maximum bending moment. Now, let us look into the cases that how do we compute the maximum bending moment. Now, when you have this particular beam where you have the support, hinge support and the roller support, and you have the uniformly distributed load acting over the entire span along with the load P over here. Now, there could be two cases, since we do not know the value of the P. Now, the shear force diagram can be of like at this point it goes over here, then now if you take a section, in fact you can place the shear force V is equals to the load W times X minus this reactive force. Now, what happens is it goes, then since you have uniformly distributed load, it comes down, then at the load point it comes down, then further it goes down and comes over here. There could be a diagram something like this, wherein we will get a 0 shear force here at some distance. Let us call this as x. Or we can have a situation where this may not, shear force may not be 0 at this particular place, it will go here, then it comes down, at the load point it crosses, it comes over here and then comes like this. So, the shear force diagram could be like this as well. Now, if we consider this particular case, that at a distance x somewhere the shear force equals to 0. Now, we are trying to find out a point where shear force is 0, because of the fact at that particular point we know that the bending moment will be maximum. So, the bending moment could be maximum where the shear force is equal to 0, or it could be maximum where there is a changeover from the positive to the negative or negative to the positive sign. Now, we have these two possible cases in this particular case. Now, if we write down the expression for V, which is the function of P and then the distance x, and if we set this equals to 0, correspondingly we can get a value of P, and the value of P which we get, that if we substitute in the expression for x, now the value of x which we get corresponding to this, we find that it goes beyond the length of this particular beam. Now, this indicates that this kind of diagram is not possible. That means, the shear force does not cross the baseline at intermediate point before this loading P. Hence, this particular diagram will be applicable in this particular case, and hence this is the point where we expect that there will be maximum bending moment in the beam, and we compute now the maximum bending moment at this particular point, and correspondingly we find out that what could be the loading. So, if we compute the value of the bending moment there, let us say that is the point C, the bending moment at C is equals to, we have, if we take the free body diagram, we have the reactive force RB, or this is RA, and this uniformly distributed load of intensity 3 kilonewton per meter, and this is our distance x, and we have the shear force and the bending moment at the cut. So, if we call this as moment M at C, so moment at C is equals to RA times x minus 3 x square by 2. Now, RA as we know is equals to 7.5 plus P by 5, this times x minus 1.5 x square. So, this is the magnitude of the bending moment. Now, as we know that sigma is equals to m y by I, or rather sigma equals to minus m y by I. Now, here m is positive and y also is positive. So, the top will have the compressive stress. Now, since this particular cross section is a symmetrical section with respect to both x and y axis, so the top will have the compressive stress, bottom will have the tensile stress, and the magnitude wise they will be same. So, we disregard the sign over here and we take the value of the m only, and sigma has to be restricted to 10 megapascal. This is equals to, this is the expression for the bending moment, which is 7.5 plus p by 5 into x minus 1.5 x square, and as we have seen that the maximum bending moment will be occurring at the point of the load, and which is at a distance of 4 meter. So, if we calculate the bending moment at that particular point, we get, substituting the value of x as equals to 4 meter, we get the bending moment as 6 plus 4 p by 5, so much of kilonewton meter, assuming that p is in kilonewton. Now, if we substitute the values in this particular expression for stress, now m is 6 plus 4 p by 5 into 10 to the power 6, so much of Newton millimeter, into y is the furthest distance from the neutral axis. Now, neutral axis divides the whole section into two halves. So, this distance is 200 because the total depth is 400, this divided by the moment of inertia, which is 120 times 400 cube by 12. So, my by I is equals to stress. Now, from this if we compute the value of P, we get the value of P as 32.5 kilonewton. So, this is the largest value of P that we can apply, so that the level of stress is within 10 megapascal. It does not exceed the value of 10 megapascal if we limit ourselves to 32.5 kilonewton load. Now, let us look into another problem wherein the load uniformly distributed load of intensity Q is acting, the uniformly distributed load is acting over a distance of 2 meter, which is a partial loading, and the cross section of the beam is a circular one having a diameter of 50 millimeter. Now, what we need to do is that maximum load Q that can be applied on this beam, so that the bending stress is limited to 50 megapascal. So, here we will have to find out the value of the load Q, so that the stress does not exceed a value of 50 megapascal. Now, again as we have done earlier, we will have to find out the value of the maximum bending moment. So, we again resort back to the drawing of the shear force and the bending moment diagram, so that we can get a clear picture of what is the value of the maximum bending moment and at which location that occurs. Now, to do that, what we need to do is that we need to compute the value of the reactive forces as usual, and if we do that with respect to this particular beam, now again we take the free body of the beam, HA as usual equals to 0, and if we compute the value of RA and RB, let us call this as RA and this as RB. Now, RA plus RB is equals to the vertical load is twice Q, and if we take the moment of all the forces with respect to B, we can get the value of RA is, which is twice Q times 1 divided by 3. So, this gives us 2 Q by 3, and correspondingly RB is equals to 4 Q by 3. So, these are the values of the reactive forces. Now, if we take a free body of this left segment between 0 to 1, then we have reactive force RA over here, we have the shear force and the bending moment V and M. Now, V plus RA equals to 0, so this gives you V as equals to minus RA. RA again is equals to 2 Q by 3. So, from 0 to 1 we have the constant value which is equals to 2 Q by 3, but it is negative. Now, at this section, in this segment between 0 to 1, the value of the moment M is equals to RA into X. So, it varies linearly with X. When X equals to 0, the bending moment is 0. When X is equals to 1, the value of the bending moment is equals to 2 Q by 3, so much of kilonewton meter. Now, let us take another segment which gives us the value from 1 to 3. Now, if we take the free body diagram of that particular part, we have the reactive force over here. Now, we have the uniformly distributed load which is 1 meter away from this end, and at this section again we have V and the bending moment M. Let us call that this distance as X. So, here the value of the shear force V, if we take the vertical equilibrium, V plus RA minus W into X minus 1, this is equals to 0. So, V is equals to W into X minus 1 plus RA, RA is equals to 2 Q by 3. I am sorry, this is Q, Q is the uniformly distributed load. Now, when X is equals to 1, B is equals to 2 Q by 3, as we have seen, this is minus 2 Q by 3. Now, when X is equals to 2, then this is Q, I mean X is equals to 3, then it is twice Q, and this is also twice Q by 3. So, this gives you twice Q minus twice Q by 3, which is equals to 4 Q by 3. So, here at this end is equals to positive 4 Q by 3. Now, as you can see that we at this point we had minus 2q by 3, at this point we have plus 4q by 3. When x is equals to 3, we have 2q minus 2q by 3, which is v equals to 4q by 3. Now, so it changes from minus to plus, so somewhere we will have a 0 value. Now, if we substitute the shear force value as equals to 0, then we can get the value of x. So, setting v is equals to 0, this we get qx minus q minus 2q by 3. So, we get that 5q by 3 is equals to qx. So, this gives us that x is equals to 5 by 3, which is from the left end. So, at a distance of 2/3 from here, we get the 0 shear force, and this is what is indicated over here. So, from a distance of 2/3 meter from here, we get the shear force as 0, and it is expected that the bending moment at that particular point will be the maximum. Now, this particular moment of course will be a continuous one without any kink. Now, from this point to this point, since we have uniformly distributed load, and as you can see now, the if we take the equilibrium of the bending, the moment calculation if we carry out over here, then the bending moment equation comes as m then minus R A into x, then plus q, this is x minus 1. So, x minus 1 square by 2, and this is equals to 0. This is the expression for the bending, and this is since square of x is a parabolic distribution, and as we have seen that when x is equals to 5 by 3, then the shear force is 0. So, setting x as equals to 5 by 3, we will get the value of bending moment, which we get m as equals to 8q by 9. So, we get the value of the bending moment as equals to 8q by 9, and this is a positive bending moment right through. So, you see that when we like to find out the bending stress in a beam, we have two clear parts. First part is that we will have to draw the bending moment diagram to know how the bending moment varies over the entire length, whether there is any change over in the sign of the bending moment or not, and then it will give us that what is the maximum value of the bending moment and at which location that maximum bending moment is occurring. Now, once we have that particular information, then we can compute now the stress based on the cross sectional information that we have. So, first step we have done, that we have now known the maximum bending moment is equals to 8q by 9. Now, if we look into this particular configuration, that the cross section of the beam is a circular one, and the neutral axis lies at the centroid of the cross section, which is this, which divides the section in two halves, and thereby the maximum distance y is equals to d by 2, which is equals to 25 millimeter, and the moment of inertia of the cross section with respect to the neutral axis is equals to pi d4 by 64, where d is 50, and this is the value of the moment of inertia that we get. And we have the information that maximum bending moment is 8q by 9, which is occurring at a distance of 5 by 3 from the left support. Now, if we like to calculate the bending stress sigma, which is equals to, now this being again symmetrical with respect to both the axes, now we disregard the sign, because we know for the positive bending moment the stress is compressive at the top and tensile at the bottom. We know the nature of the stress. So, what we are dealing with is only the magnitude. So, sigma is equals to m y by I, and m here as we have seen is a positive moment. So, this is equals to 8q divided by 9 into 10 to the power 6 so much of Newton millimeter, because q is in kilonewton per meter. So, this is kilonewton meter, 8q by 9 is so much of kilonewton meter. So, multiplied by 10 to the power 6. Now, y is 25 and I is equals to this, which is 306796.2 so much of millimeter to the power 4, and stress as we have seen is limited to 50 megapascal, and from this expression if we compute the value of q, we will get the value of q as 0.7 kilonewton per meter. So, this is the intensity of the load, the maximum intensity of the load that we can apply on the beam, so that the stress is within 50 megapascal. It does not cross the value of 50 megapascal. So, this is the value of the intensity of the load that we can apply on the beam. Well, now let us look into another example problem, wherein the cross section of the beam is an unsymmetrical one, unsymmetrical with respect to the horizontal axis, but it is again symmetrical with respect to the vertical axis, and the beam is subjected to 3 concentrated loads, P over here, 3P at the center and P over here, and please note that it is hinged at this particular end and is on roller support over here, has overhang on this side as well as on this side, and the geometrically it is symmetrical, and of course loading wise also it is symmetrical. Now, what we need to do is that we will have to find out the maximum value of P if the bending stresses are not to exceed 40 MPa in tension and 100 MPa in compression. Now, in this particular case, as you can observe that in the previous 2 occasions where we had dealt with a rectangular cross section or a circular cross section, both the sections are symmetrical with respect to both vertical and the horizontal axis, and we did not bother about the stress limits like compressive and tensile stresses, because we knew that the magnitude of the stresses that will be developed because of a bending moment at any section, they will be the same, because the value of I and Y will be the same at the extreme points. Now, if we have a cross section which is not symmetrical with respect to the horizontal axis, and thereby there will be the difference in the Y values with respect to the neutral axis of the extreme fibers at the top and the bottom, and consequently there will be change in the bending stresses. So, if we will have to know precisely what is the allowable stress in tension and compression we can have, so that we can check the member whether they can withstand that load it is subjected to. Now, in this particular case we have these loads which are acting P, 3P and P. We will have to find out the maximum value of the P, so that these stress limits are not exceeded. Now, to do that again we will have to first find out that what is the maximum value of the bending moment that can occur in this particular beam at any point along the length of the beam because of such loading, and at which location such maximum bending moment occurs. Now, to do that, as we have done earlier, let us again compute the value of the reactive forces, and if we compute the value of the reactive forces, this here we call this vertical reactive force as RB, this as RD, and as usual, since there are no horizontal forces, so horizontal force at the hinge support is equals to 0. So, RB plus RD is equals to the vertical forces which are equals to 5 times P, and since they are symmetrical, so RB and RD will be equal in magnitude, and this is equals to 2.5 P. Now, if we look into the shear force diagram, see between A and B in the first segment, if I take a section over here, the value of the shear force will be equals to P. B is equals to positive P. So, and from A to B there is no other loads, so it is constant. So, the value of P is constant, the shear force between A and B. Now, if I take a section between B and C and draw the free body diagram, we have the load here which is P, we have the reactive value which is 2.5, and we have the shear force which is V, and of course we have the moment. Now, V plus R A minus P is equals to 0. So, this gives us V as equals to P minus R A. Now, R A is 2.5, so this is 2.5 P, so this is equals to minus 1.5 P. So, from plus P to it goes to minus 1.5 P at this particular point. So, this is what is indicated in this diagram, this is 1.5 P. Now, between B and C, since there are no loads, so the 1.5 P continues up to the left of this load at C. Now, if we take a free body diagram taking a section over here, then we have the concentrated load P acting here, we have the reactive force R B over here, we have the concentrated load which is 3 P over here, and at this section we have again the shear force V. Now, if we take the vertical equilibrium of the vertical forces, we have V plus RB, and they are in opposite direction. This is equals to 4P and RB is equals to 2.5P. So, B is equals to plus 1.5P. So, you see immediately after C, before C we had minus 1.5P, immediately after C, after the concentrated load P, we have a change shear force which is equals to 1.5P plus 1.5P, and again between C and D, since there are no loads, so it continues up to with 1.5P, and then again at reactive force RD, again it is 2.5P. So, if we take a section over here, we get immediately after this support a shear force which is equals to negative P. So, it comes down from plus 1.5P to the plus P, and then again it continues over here. At this point we have the force P. So, this is the shear force diagram as we get, and as you can see along the length of the shear force diagram, we have 3 places where the shear force has changed sign from the positive to the negative or negative to the positive. So, at these 3 locations we expect that there will be the values of the bending moment which are of maximum in nature. Now, the question is, if we compute the values of the bending moment at these sections, then you will find that we get a value of P kilonewton meter at this particular point. We get a bending moment of 2P kilonewton meter at the central point, and at this point again we get P kilonewton meter which is minus at this particular point. Now, from this bending moment diagram, if we look into, you will find that we have a value of bending moment P which is negative, here the value of the bending moment which is positive. So, along the length of the beam at 3 locations we are getting the magnitudes, this being symmetrical. On the either end at the supports we have a negative P kilonewton meter as the moment, and at the center we have plus 2P kilonewton meter as the moment. And mind that the moment which we are getting at the center is a positive moment, and at the support it is a negative moment. Hence, we say that the maximum positive moment is 2P kilonewton meter and maximum negative moment is P kilonewton minus P kilonewton meter. So, if we deal with these 2 moment values, now we have identified that we have a maximum positive moment as equals to twice P and maximum negative moment as equals to P. And mind that when we have a positive moment, the positive moment is in this particular direction, causing a compressive stress at the top and tensile stress at the bottom. When we are dealing with the negative moment, we have in this form where tension is at the top and compression is at the bottom, and since the section is unsymmetrical, the value of y1 and y2 will be different, and consequently the values of the stresses will be different, and since we have different allowable stress for tensile and compressive, naturally we will get 4 values of P corresponding to all these 4 criteria. Now, first if we try to locate the centroid of this particular section through which the neutral axis will pass through, if we take the moment of all the areas, say with respect to the top, the distance y bar, we get y bar as equals to 87.5 millimeter from this bottom face, and consequently this is 225. So, 225 minus 87.5 will give you 137.5 over here, and if we calculate the moment of inertia about this neutral axis, you will get a value of this which is 37.9 into 10 to the power 6 millimeter to the power 4. Now, if we try to compute the stresses corresponding to these 2 moments, first let us take the value of 2P. Now, sigma as we know is equals to minus m y by I, and by saying minus we know that for the positive moment we will have the compression at the top. So, this is equals to 2P into 10 to the power 6 so much of Newton millimeter times y. Now, when we are computing the stress at the top, y is 137.5 divided by I is equals to 37.9 into 10 to the power 6 so much of millimeter to the power 4. Now, this is the stress at the top which is compressive in nature. So, we have this as equals to 100 MPa. So, this if we limit to 100 MPa, then correspondingly the value of P which we get is equals to 13.8 kilonewton. Now consequently we calculate the tensile stress at the bottom corresponding to this moment, and tensile stress is 640 MPa. So 40 MPa is equals to twice P into 10 to the power 6 into 87.5 divided by I, which is 37.9 into 10 to the power 6. Now from this if you compute the value of P, this comes as equals to 8.66 kilonewton. Now these are the two values of P which we have obtained corresponding to the compressive and the tensile stress. Likewise, if we compute the value of the stresses corresponding to the this negative maximum which is equals to P, this will produce a tensile stress at the top and compressive stress at the bottom. Now if we try to compute the value of the stresses from which we can get the value of P. Now again the tensile stress at top, which is equals to 100 MPa, is equals to P into 10 to the power 6 into Y, which is at the top, which is 137.5 divided by 37.9 into 10 to the power 6, and this gives us a value of P as equals to 11.03 kilonewton. Now if we compute the stress at the bottom, which is a compressive stress, which is equals to 100 MPa, well this was tensile stress, so this was equals to 40 MPa. Now if we take the compressive stress at the bottom, which is equals to 100 MPa, equals to P into 10 to the power 6 into 87.5 divided by 37.9 into 10 to the power 6, this gives us a value of P as equals to 48.31 kilonewton. This is a 43.31 kilonewton. So now you can look into that we have four values of P, and this is 43.31 kilonewton. Now we have four values of P, out of which the minimum one will be governing, and the minimum value of P which we get from these stress considerations, they are P as equals to 8.66 kilonewton. So this is the value of the P which can be applied, so that the stresses within the will be within the limit for this particular cross section. Well, I have another example problem for you. This you can try that. This is a beam which is subjected to a uniformly distributed load of total W kilonewton per meter, and at this point we have a load of W having a cross section for which the distances from the neutral axis are given and the moment of inertia with respect to the neutral axis is given. You will have to compute the value of W so that the stresses do not exceed the limiting values. Now to summarize, then, in this particular lesson we had recapitulated the aspects of the previous lesson. We have looked into the effect of bending stress on beams with different cross sections. Of course the sections are symmetrical with respect to the vertical axis, but it could be unsymmetrical with respect to the horizontal axis. And then we have looked into the concept of economical section, and also we have solved some examples to evaluate bending stress in beams. Now the questions for you are: what is the impact of bending stress in arriving at a size of a beam? What is the relation between curvature and the bending stress in a beam? And what is meant by section modulus? We will give the answers for these questions in the next lesson. Thank you very much. Welcome to the third lesson of the sixth module, which is on stresses in beams part 3. In fact, in the last two lessons on this particular module, we have discussed aspects of the bending stresses in beams. Now in this particular lesson we are going to look into some more aspects of the stresses, and in fact we will be looking into the effect of the shearing stress in beams. So it is expected that once this particular lesson is completed, one should be able to understand the concept of shear stress in beams of rectangular cross section. One should be able to derive the shear formula, the formula for evaluating